last few lessons, we have discussed ways in which people have invested money into accounts that are earning interest, both simple interest and compound interest. For all of these examples, though, all we've done is we've put in one principal payment and let it run for a period of time and then calculated the amount that was left at the end of the period. Interest was accumulated throughout, but in the real world this isn't really how things work. People don't just put one payment into an account. A lot of times investors will make what we call regular payments. So either every month or maybe every other week, they'll put money into an investment, and then all of those different payments they put in will all add up, but all of them will also earn interest. These types of investments are called annuities. So in this course we're going to be examining something called ordinary simple annuities, where we make payments at the end of each compounding period. If we compound 12 times a year, then we're going to be making 12 payments per year. Here's a question we're going to investigate first. Colin is awarded $500 per year as long as he maintains a certain average mark for each of his 4 years of high school. He plans to deposit this award at the end of each school year into an account that pays 4% per year compounded annually. So here are the questions we want to answer. Assuming that Colin maintains the necessary average, how many times will he receive this $500? And will each of these 500 deposits earn the same interest in dollars? So we're going to see if we can explain the answers to those. After that, we're going to try to determine a method to calculate how much will be in Colin's account when he graduates. Just remember that he will receive another $500 at the end of each year. Well, let's start with question 1a. So it says, assuming that he maintains the average, how many times will he receive $500? Well, if he's rewarded $500 at the end of every year for 4 years of high school, this one seems pretty obvious, but he's going to earn it 4 times. Now, if we think about it, at the end of his first year of high school, I guess we'll just call it grade 9, he's going to get $500 and put it into an account right away. At the end of grade 10, he's going to earn $500. At the end of grade 11, he's going to earn $500, and at the end of grade 12, he's going to earn $500. Will each of those $500 deposits earn the same amount of interest? Well, I would assume that the amount that he earns, or the $500 that he earns after grade 9, will be sitting in the bank all the way through grade 10, all the way through grade 11, and all the way through grade 12, earning interest that whole time. Whereas the $500 that he earns at the end of grade 12, well, that will just go into the bank, but it won't earn any interest because that's the end of the term in the account. So will each of these 500 deposits earn the same interest? The answer is no. Each $500 payment will actually earn a different amount of interest. So how do we calculate how much interest each deposit makes? And then at the end of it all, how do we figure out how much money he has at the end of the account? In order to picture an annuity, it's really helpful for us to represent all these scenarios using what we call a timeline. Timelines are going to be an easy to read and easy to visualize tool to see how annuities work. Here's how it's set up. We set up a line just like this. We put the number of compounding periods at the top of the line, right here, 1, 2, 3, and 4. And then we put where we are today. So we're right here on the timeline. 1 year from now, at the end of grade 9, he's going to deposit $500 into his account. 2 years from now, he's going to deposit another $500. The same at the end of the 3rd year, and the same 4 years from now. So 4 different deposits of $500. It's safe to assume, I guess, that he will have at least $2,000 in his account at the end of the year. Or at the end of 4 years. It's safe to assume that he will have at least $2,000 in his account at the end of 4 years. His $500 deposits 4 times. But now let's figure out how much interest each of these deposits makes. Well, let's start from the very end. This $500 deposit won't earn any interest because it's at the end of the term. So it's just going to sit in the bank account as $500. But these other 3 deposits of $500 will each earn interest. At the year 3 $500 will earn interest for 1 whole year, going from year 3 to year 4. So we could say that we'll earn 500 times 1.04, since our interest rate is 4%. So whatever 500 times 1.04 is, that's how much money will be in the account from this $500 deposit. The $500 deposit after year 2, well, that'll earn interest for 2 years, all the way to year 3 and all the way to year 4. So we write that as 500 times 1.04 to the exponent 2. And then the same thing for the $500 deposit after 1 year. It's going to earn interest for 3 years, so we write 500 times 1.04 to the exponent 3. And so our total amount is going to be all of those added up together. 500 plus 500 times 1.04 times 500, plus 500 times 1.04 squared plus 500 times 1.04 to the exponent 3. And we end up with, if we add that all up, $2,123.23. We said it had to be at least $2,000, and so you can see that we earned $123.23 in interest over those 4 years. Now, if we look at this right here, what does this look like to you? Think back to our sequences and series unit. What type of series is this? Well, I guess we can ask ourselves, is it arithmetic or geometric? And so the answer to that is, are we adding the same amount to each term, or are we multiplying the same amount to each term? And as we go from the first term to the second term, and the second term to the third term, notice we keep multiplying a 1.04. So this has to be a geometric series. And here's the formula we use for geometric series. So I guess we can come up with a formula to help us figure out how much interest will be a result, and what the total amount will be at the end of this annuity based on the formula for geometric series. For our example, our A value was the first term, which was 500. The common ratio was what we multiplied to each term, so that's 1 plus I. And in our example, I was 0.04. And so if we sub those things into our formula here, instead of saying Sn, we can just say A for amount. And so we plug all those numbers in, and this is what we end up with as our formula. 500 times 1 plus I to the exponent n minus 1 all over I. And if we put in I equals 0.04, well, we end up with A is equal to 21.23 and 23 cents. Exactly what we had before. And so this leads us to our general formula for an annuity. For any annuity where R represents the regular deposits, I represents the rate of interest, and N represents the number of compounding periods, we can find the future value of an annuity as this equation. R times 1 plus I to the exponent n, subtract 1, and all of that over I. We're going to look at 2 different examples. Example 1. At the end of every month, Yoshi deposits $100 in an account that pays 6% per year compounded monthly. He does this for 3 years. So we're going to draw a timeline to represent this annuity. And then we're going to try to determine the amount in the account after the 3 years. And then how much of that amount is interest that the annuity had earned over those 3 years. Well, let's start with his timeline. So I have the line already drawn here, but let's throw on our various points that we're going to use. We're going to start with now, or where we are today. The top here will represent our compounding periods. If he's depositing $100 at the end of every month for 3 years, there's going to be 36 total compounding periods. Well, I don't want to write 36 compounding periods here. So what I'll do is I'll put the very last one on the timeline, the 36th. And on my timeline, I'm going to put the first couple. So 1 month, 2 months, and then I'm going to put the last couple. So the 35th month, the 34th month, and I'll even put the 33rd month. And then in between, we have all those other months. So 3, 4, 5, all the way to 32. And we just don't need to represent them. Our timeline will account for them. I'm also going to write that our compounding periods, just so that we know, are in months. Okay, on the bottom, we write down what our deposits are. So after the first month, we're going to put in $100 into the account. After the second month, we're going to put in another $100. And this will continue all the way through month 33, month 34, month 35, and you're going to include one on the very last month too, month 36. So to determine how much each of these $100 deposits makes in interest, we're going to start at the end. The last $100 deposit won't earn any interest because it was put in at the very end. So this is still going to equal 100. The second last one, or the one that was put in on the 35th month, well, when we bring this forward to the 36th month, it will earn interest for 1 month, or we can say 1 compounding period. So this will equal 100 times, and our interest rate, remember, was 6% per year. But it's compounded monthly. So we need to figure out our I value before we can put this into our timeline. 6% is 0.06. And if I'm dividing it, or compounding monthly, I'm going to divide by 12. And so this gives me an interest rate of 0.005. So this $100 deposit will earn 100 times 1.005. The $100 that was deposited on the 34th month, or the 34th compounding period, well, it's going to earn interest for 2 compounding periods. So when we bring it forward to the very end, it's going to be worth 100 times 1.005 to the exponent 2, because it's in there for 2 compounding periods. And we're going to continue this pattern of bringing deposits all the way forward to the very last compounding period and writing out what their or what the formula would be to figure out how much they're worth. The second last one will come all the way forward here, and it will earn compounding periods for 34 different compounding periods. So this is going to be worth 100 times 1.005 to the exponent 34. And last but not least, this 100 will get 100 times 1.005 to the exponent 35. We're going to put a little ... here just to tell us that these payments, or these amounts, will continue in between those different ones. Okay, so now let's use our formula to determine the amount in the account after 3 years. Remember, the formula is future value equals R times 1 plus I to the exponent n minus 1, and all of that divided by I. Our regular payments were $100. Our interest rate was 0.005. N is the number of compounding periods, so that's 36. Subtract 1. And then divided by I, but not 1 plus I, just I. So 0.005. Once we plug all that into our calculator, this is what we get. 100 times, and then in brackets we're going to put 1.005 to the exponent 36 minus 1, and then all of that divided by 0.005. $3,933.61. That's a ton of cash. Now let's just make sure that this sort of makes sense. He puts in $100 deposits every month for 3 years. Well, that's 36 total months. So 36 times 100 is 3,600. Well, this sort of does make sense. His future value is $3,933.61. So what's the total amount of interest that he earned on this account? So 3,933.61 subtract the 3,600 that he himself put in, and we're left with an interest amount of $333.61. That's not bad. I'd like to earn $333.61 just for putting money into a bank account. Here's example 2. Peach needs $4,000 for university tuition when she graduates in 2 years. She plans to make deposits into an account that earns 6.5% per year, compounded bi-weekly. So draw a timeline to represent this annuity, and then figure out how much she should deposit bi-weekly into the account so that she'll have $4,000 when she graduates. Alright, so before we draw the timeline, I'm going to get the interest out of the way. It's 6.5% per year, but it's compounded bi-weekly. Remember, bi-weekly means every other week. So there's 52 weeks in a year, so every other week means that it's compounded 26 times per year. So her interest rate is going to be 6.5%, which is 0.065 divided by 26. 0.065 divided by 26 is 0.0025. On our timeline, we're going to have today, which we'll just say is now. We're going to have our different compounding periods. And our compounding periods this time are bi-weekly, so that's what we'll write. Compounding periods, which we're going to say are bi-weekly. Well, how many compounding periods are we going to have? It's every other week for 2 years. Well, 1 year has 26 compounding periods, which means 2 years will have double, or 52 total compounding periods. So the very last compounding period will be the 52nd one, which means I'm going to have a 51st one, I'm going to have a 50th one. This will continue all the way until I have my second, and then I'll also have my first. As for the deposits, this is what I'm trying to find. So I don't know what my deposits are yet. So I'm going to write that my deposits are just R, my regular deposits. They're all going to be the same, but I don't know what they are yet. Each of these regular deposits are going to be brought forward to the very last compounding period. So the 52nd one will just be whatever it's worth, R. The 51st one will be brought forward and be worth R times 1 plus I. Well, I is 0.0025, so times 1.0025. This regular deposit will be brought forward 2 compounding periods, so 1.0025 to the exponent 2. And we'll keep this going for these last 2 here. So dot dot dot. This will be R times 1.0025. And how many compounding periods will this one have? Well, we know that this compounding period is the second one, which means there are 50 more, because I need a total of 52. So this will be to the exponent 50. And last but not least, my very first deposit will be brought forward, and it will be in the account for 51 compounding periods. And that's how you make a timeline. So now how much should she deposit bi-weekly? In the previous example, we figured out what was in the account after the end of the term, but we know that she wants to have $4,000 at the end of the term. Our question is, how much does she need to deposit each compounding period? So what we're going to do is we're going to set up our formula. Remember, our formula is future value equals R times 1 plus I to the exponent n minus 1 all over I. Our future value we know, it's $4,000. That's what she wants. The R we don't know, so I'm going to keep that as R. I we know is 0.25, so this is going to be 1.0025. And it's going to be in there for 52 compounding periods. Subtract 1, and then all divided by our interest rate, which was just 0.0025. Well, let's get our calculator out and figure out what's in these square brackets. And then we'll divide it by 0.0025, and then divide that whole thing on the other side to isolate for R. But let's start with what's in the square brackets. Alright, so 1.0025 to the exponent 52 equals 1.138643 and so on. And then we're going to subtract 1. So I get 0.138643666. So let's write 4,000 equals R times 0.1386436. 466. I don't want to miss any of these decimal places because it could affect my final answer. And then all of this divided by 0.0025. So because I want to isolate for R, I'm going to take my 4,000, multiply it by 0.0025, and then divide it by this answer that I got here. So 4,000 multiplied by 0.0025, but then divided by 0.1386436,466. And I end up with $72.13. And remember, what you just found was you found the regular deposit that Peach would need to make every other week in order to have $4,000 at the end of 2 years. So all she needs to put in every other week is $72.13. Now, for you, if you have a part-time job, does that seem reasonable? Do you earn enough money to put in $72 every paycheck? Well, if you did, and you did that for the next 2 years, you could have $4,000 saved up. And that might go a long way towards your tuition, or towards a computer, or towards a new used car, or whatever you might need to buy after you graduate high school. So just think about that. And that's it. Those are annuities. In the next lesson, we're going to learn about the present value of annuities. So we're going to look at questions like, if I need to pay somebody $10,000 and I'm going to pay them $1,000 per year over the next 10 years, I don't necessarily need to have $10,000 today. I just need to have a chunk of money in an account that'll earn interest, but I can deduct $1,000 every year so that at the very end I'll have $1,000 left over to pay him for the last year. So the question is, how much would I need today in order to be able to fund that? That is a present value annuity, and we're going to look at that in the next lesson. See you then.